Hi, good morning, and welcome to the Quantum Computing Weekly Recap for December 28th. Today we're going to talk about some insane stock growth, interesting new algorithms for chemistry and error correction, and then a new company that got announced. So let's get right into it. For the first story of this week, I want to talk about some quantum stocks that are incredible performers recently. IonQ, Rigetti, and D-Wave are feeling the shockwave of Google's announcement with their Willow chip and their error correcting qubits. And the whole market is kind of rising with this latest news and research. For example, IonQ, D-Wave, and Rigetti are up 206, 582, and 789% respectively, which is just an incredible amount. I'm really excited about this because more money going into these companies means more research, more funding, more growth. It'll be very good for the quantum community as a whole and quantum companies as well. So I'm very happy that the stocks are so high recently. I hope that it isn't hype, but people are actually recognizing the benefits of quantum computing and how close we are. So this is a great time. I hope you're all invested in quantum because this past week has been really crazy. Shifting gears a little, I want to talk about some research that came out of Rice University about a new way to do molecule simulation. In the past, what we did is we used VQE, and VQE variational quantum eigensolvers are a great method for doing molecule simulation, but they don't scale very well. If I want to simulate how photosynthesis works, for example, I have to have a very, very big computer, a lot of qubits. But for the Rice researchers, with quantum simulation of molecule electron transfer, what they were able to do is use trapped ion systems and demonstrate real-time spin dynamics. So what they're doing is, and I think it makes sense to use a trapped ion system, is they are able to more effectively simulate what the molecules will be doing using those ions. And they were doing this kind of simulation with quite large atoms, ytterbium atoms, 171 and 172. So very large atoms, and they were able to get quite accurate in non-adiabatic, which means you're allowing heat and more complicated dynamics into the system. And we can see the goal and what they measured. So there's a little bit of a difference here, master equation versus what they measured. But when you go to an adiabatic system, that is a lot more simple. You're just kind of dealing with the dynamics, not allowing heat and different things into the system. The lines will almost match up perfectly. I mean, this algorithm they created is very accurate, and it kind of opens up an entire realm of possibility for molecule simulation. For example, and the article talks about this, but a big application would be photosynthesis. So it's kind of accepted as an extremely important thing to simulate on a quantum computer because it's impossible to simulate on a classical computer. And if we can understand photosynthesis, we could even build nanostructures that could suck the carbon dioxide out of the air, split it, and create oxygen very cheaply. So this kind of opens up an entire realm if we can leverage this new algorithm with larger quantum computers like, Google and different neutral atom companies like QuEra, and maybe IBM's too with error correction. This whole kind of benefit of modeling very complicated processes that happen in nature become possible. I do think, though, that either neutral atoms or trapped ions are a good step forward because you are simulating atoms with atoms, which makes a lot of sense. For all of the other like qubit technologies, you're trying to keep a manufactured atom very happy in its quantum state. Like, it's very difficult to do that over long periods of time. It makes a lot of sense to use a actual ion or neutral atom or whatever to do this computation. Use nature to simulate nature, as like Feynman sort of said. We have another very exciting algorithm. This one is actually very special because they kind of reimagined what quantum error correction looks like. And if you saw a couple weeks ago when we talked about Google's release of their Willow chip with quantum error correcting codes, 3x3, 5x5, 7x7, I think, of arrays of qubits, this kind of takes a different approach. So what they're doing is they're calling, and this is a team out of QuEra, they're instead of working on kind of these gates that balance and correct each other, what they're doing is they're creating magic states. And what this looks like is each of the different qubits get put in this magic state. And when they do math over the magic states actually error correct each other. So it's changing the paradigm from let's use gates to correct to let's use states to correct. And it could be thought of maybe as you're changing the entire fundamental level at how quantum error correction works. This is very exciting, I think, for neutral atoms and for trapped ions and these kinds of systems that work in a similar way with just using atoms in different arrays that you can move around. I think particularly neutral atoms are great with this because they have arrays of qubits. So I'm very excited to see where other companies take this research, where universities take it. What does it mean as we scale up? How many qubits is required for a perfect magic state error corrected qubit? It would be great to see that a lot of these algorithms hopefully require fewer qubits to get perfect states. One of the big reasons why we say that useful quantum computing, like a Shor's algorithm or some crazy big huge requirements, millions of perfect qubits. Maybe this research and more like it will drive that number down to being 100,000 or a couple 100,000 qubits to do massive algorithms. So we're going to see in the future, but this was amazing research out of QuEra. Congratulations to them. Their neutral atom platform is very special. So it's awesome to see this new kind of paradigm coming out of their unique platform. For the final news of today, we have the Nanyang Technological University and National University of Singapore creating a startup. And the startup is very interesting because they are taking control electronics. So they're trying to be at that level where you do quantum stuff you do quantum stuff, they're going to be at the level where you take that quantum stuff and make it classical. So that would be, for example, you have trapped ions and you take a picture of them and you resonate them. They release photons, you take a picture, you get, some bright splotches and some dark splotches. That is the classical layer. So it's called control electronics, and they do it for every single quantum computer. You have to have something going on quantum, you have to measure it, you have to send it to a computer. That measurement and sending is kind of what they're going to be making an entire company off of. And they actually released their first product, and it doesn't look too exciting, but it's very cool because each of these little jacks will take a microwave signal, radio signal, photon signal, whatever, from the QPU. So each of the different chips on the QPU, all those wires come up and they wire into this little control box. That control box will then, give you the results, do maybe amplification on the results. You're able to program it more easily. And a massive part of development and engineering for all hardware companies, all quantum hardware companies is, okay, we have this amazing quantum idea. Oh shoot, now we have to build control electronics on top of it. And then we have to build a cloud on top of it. So it's these people really want to build a quantum computer, and then what they do for probably 2/3 of the time is build the systems around that quantum computer. So CHRONOS-Q is trying to solve that by saying, okay, build your quantum computer, stick our thing on top, and you're good to go. So I'm excited to see that this is a hardware company coming into the space that is building classical hardware to address a quantum problem. And I think that, this entire kind of idea could be applied in a lot of different places in the quantum computer. So I'm hoping more companies come out, more startups, very cool ideas emerge using this we'll handle the classical difficulties to give you all the time you want to build the quantum to the best that you can. So amazing job. I'm very happy that they spun out into a company, and I hope more companies, follow in their steps. Thank you so much for listening to this week's Quantum News Recap. I hope you enjoyed. If you did, like, subscribe. I will be posting every Saturday. And if you didn't, let me know in the comments why, and give it a downvote so I can improve the next video. If you have any questions, let me know in the comments. I'll always respond. And if it's a really interesting question, I can touch on it next week as well. Bye, you guys.